Okay, great. And our next speaker is Andrea Schincaglia from the University of Ferrara.
Thank you so much. Well, thank you to the organizing committee first for the great work you did for this workshop. And it's actually my first oral ever, and it's great to be in this great venue. So thank you so much. So I am Andrea Schincaglia from University of Ferrara, Italy, and I'm currently visiting PhD here in Belgium at the Gembloux University of Liège. So today I'm gonna guide you really quickly through a tour to the chromatographic fingerprint of Pistacia vera fruits. So Pistacia vera is a plant that origins in areas that nowadays correspond to Iran and Afghanistan, and it's really interesting to know that some remnants of these of pistachio nuts have been found in this area, and they date back to the 6th millennia before Christ. So what's the fruit of Pistacia vera, right? So botanically speaking, the fruit is a drupe like apricot or peaches. But on the contrary to what happens for apricot or peaches, we are not interested in the outer freshly part. We are interested in the kernel. So after the harvest, the outer layer is removed, and we collect the kernel that are dried naturally. And after this drying process, we have what we all know as pistachios, so our final edible products. To give you an idea of some numbers about pistachios, we can see that last year 795.3 thousand metric tons of pistachios were produced. The leading producer are the United States, in particular California, followed by Iran and Turkey. And you can see Europe is just right there, a small 1%, 2%. The export reflects the internal production of the aforementioned countries, with the United States, Iran, and Turkey on the top 3. And interestingly, in 2020, one person on average consumed 0.13 kilos of pistachios. But why pistachios are important for us? Well, first of all, they are functional food. They are important for our health, really good for our health. In terms of endothelial function, they help us to control the glycemic, and they are also great antioxidant and anti-inflammatory. When it comes to food industries, usually they require high quality standards of the raw material, because even the raw material is rather expensive. And why are we interested in the volatile profile? Well, first of all, we can differentiate based on the geographical origins. That's what we did, our goal. We can see if pistachios underwent post-harvest treatment. We can evaluate the oxidative stability, spot eventual frauds, as Tatiana pointed out before. And let me spend a few words on contamination. So I don't know if you are aware that pistachios, among other food commodities, can be infested by Aspergillus flavus and Aspergillus parasiticus. So these fungi can produce aflatoxins that are really carcinogenic compounds, and we can't get rid of those. Unfortunately, it's really, really difficult. So it has already been pointed out, discovered that the volatile profile of pistachios can be affected by the mold infection, but has not been demonstrated that there are real differences in the volatile profile from pistachios contaminated by aflatoxin-producing fungi and non-aflatoxin producing fungi. So we want to bridge this gap, find these differences through the use of high capacity sorptive extraction and GC time GC. So This is our final goal, but let's stick with the geographical origin for the moment. So here you can see the origin of pistachio we have available. We collaborate with a great company from Sicily that provided us certified pistachios from these origins, and we would like really to thank them. So we have samples from Sicily, Spain, Iran, Turkey, and California. What was our workflow? So we evaluated the size of the sample. We performed an optimization of the headspace extraction. I will then show you some of our preliminary results and our future perspective. So let's start first with the sample size evaluation. So when we are working in headspace extraction, we have always to take into account that there are two equilibria among the three phases going on. So we have an equilibrium between our sample and the headspace, and an equilibrium between the headspace and the fiber. So theoretically speaking, the amount extracted by the SPME is proportional to the initial concentration of the sample. But the direct proportionality between the chromatographic area we have and the initial concentration is verified only when we are in non-saturated headspace. So when we are in non-saturated headspace, we see that after multiple extraction, we see a proportional decrease of our peak area, and this is the condition we want to be in. So to perform multiple headspace extraction, we used, of course, SPME that let us performing this multiple headspace extraction. We used three-phasic SPME, but later on, with our analysis, we switched to this probe-like tool from Mars International called iSort, and we evaluated the coatings you can see here. So about the sample size evaluation, we scaled down from 1.5 gram to 0.5 gram using SPME. And to give you an idea of our results, you can see that after pre-extraction, basically the peak area for these compounds is always the same, it's pretty much similar. But when we arrive to 0.1 gram, we can clearly see that there is a proportional decrease of the area of this compound, and that's why we decide to use 0.1 gram of pistachios for the further analysis. So here a brief overview of our instrumentation. We have a century out sample from Mars International in line with a GC times GC triple quadruple NS. The GC system is from Shimadzu, and the field flash modulator is from Mars, from Cepsos. So just our conditions. So we used a classic set of columns, so non-polar in first dimension and polar in second dimension, a reverse field flash modulator, custom temperature program from 32 to 20 degrees at 7 degrees per minute. Of course, the triple quadruple MS was operated in single quadruple mode, and we have, of course, our chromatogram. So we also performed a design of experiment, a central composite design for the extraction of the volatile, taking into account two factors, time and temperature of extraction, and all the condition you see here were evaluated for all the coatings we have available. some results from our design of experiment. The triphasic had the best result at 30 minutes of extraction at 54 degrees. For the DVB PDMS, 7 minutes of extraction at 70 degrees. The CAR PDMS 50 degrees, 50 minutes, 55 degrees. And in the end, the PDMS at 50 minutes, 71.5 degrees. So here you can see from top to bottom the chromatogram we obtained, but probably you don't see much from here. So let's go a bit more in detail. So here around retention time 10, you can clearly see that the DVB CAR PDMS and the CAR PDMS perform better in terms of range of compounds extracted. Here between 12 and 20 retention time, you can see that actually the DVB CAR PDMS seems to perform better. And if you see the DVB PDMS, actually seems like it extracted higher quantity, but actually these compounds are all siloxanes, so they were not taken into account for the further data evaluation. And here you can probably see nothing, which is the case for DVB PDMS, CAR PDMS, and PDMS. But if we zoom in the DVB CAR PDMS, we can actually see that something here was extracted. So that's why we decided to use the DVB CAR PDMS for further analysis. And we also evaluated the complementarity among the 4 coatings, seeing that there was no complementarity. So we stuck with the DVB CAR PDMS. Here to remind you about the origins we have available. And let's see some preliminary results. So unfortunately, we don't have an adequate number of samples to perform chemometric manipulation. Although we were able to plot our early results in this heat map, where you can see, even if these are early results, that there is some clustering between the various origins we have. So here you can see a cluster from Turkey, which is really rich in terpenes, that gives this spicy and floral and herbal odors. This further cluster is shared between Turkey and Spain, rich in also here in terpenes. You can see here beta-pinene, paracetamol, and so on, giving this pine, woody, and citrus-like aroma. This cluster is, I think, is amazing because our 3 cultivar among the Mediterranean area and are rich in terms of alcohol, the 1 ethanol, 1 octanol, and 1 nonanol, meaning that the geographical origin can really be seen through the volatile, of course. California, where the pistachios most different between the other, we can clearly see that are really rich in terms of acetic acid, spirin, and oxylen, giving this vinegar and balsamic aroma. Also, pistachios from California and from Spain were rich in terms of butyrolactone, giving this creamy, milky odor. And last but not least, this cluster shared between Turkey and Iran. We really think that these branched alkanes are not coming from the pistachios, but unfortunately are coming from the packaging in which the samples were delivered. So our future perspective and our goal, Well, first of all, when we will have an adequate number of samples, we want to perform a cluster analysis, and we will then be able to catalog pistachios accordingly to the origin, not just in terms of country, but also in terms of different cultivar inside the same country. But our final goal is about contaminants, as I pointed out before. So with the power of high capacity short pivot extraction and GC/GC, we want to see differences between aflatoxin contaminated pistachios and non-aflatoxin contaminated pistachio kernel. So is everything for today. I would really like to thank both my colleagues and supervisor here in Belgium and in the University of Ferrara. Thank you so much.